cards, right? So I told you last week you can either make PowerPoints. One group, 5.8. One of the team members made the PowerPoint for 5.8. That was really good. I said, wow, this was really awesome. And then, what was your first name? Michelle. Michelle did PowerPoints for her whole section. It's really, really good, right? So it was fun, right? And then, because Chris, I love the way how she does her homework and stuff, and because chapter 5 is so important, so then chapter 5 talks about chemical reactions and quantities. And when we say quantities, chemists always work with a chemist's dozen called the mole. You know what a baker's dozen is, right? When you want to order, say, I want to get a baker's dozen of donuts, do they give you 12 or something other number? 13. They give you 13, a baker's dozen, right? So a chemist's dozen is like a mole. So we'll go ahead and have Chris and Michelle first, and then you want to add on? You want to put the names of your group, so you want to add on after?
Yeah, she told me to write it, because actually I won't be able to speak it out.
While we're talking? Okay. So let's have group 1 here, and group 2, I need you to be ready over here, right?
Take it to the father, I'm serious. Go ahead and write it. Huh? Go ahead and write it on the board.
And then
She said she wants to see this too.
That would be,
She told me she wants to see it.
and then who else is,
No. Yeah, but you don't want everybody to just there. You don't want everybody up here at the same time.
let's come down. So when you speak though, you gotta show, right? Okay. So go ahead. Oh, first, yeah.
Okay, this is our voting.
All right, we're group 1. I'm group 1's leader. My name's Christina.
Michelle, Rosalie.
And as you can see, we'll be doing a flipped classroom today with students actually lecturing the different sections of chapter 5, chemical reactions and quantities. So go ahead, Chris.
Okay, our group is doing 5.1, which is about mole. And what is a mole? A mole is a unit that contains 6.0 times 10 to the power of 23 items. 6.2 times 10 to the 23 equal Avogadro number. A mole is an element contains 6.2 times 10 to the power 23 numbers of atom. Example, 1 mole of carbon contains 6.2 times 10 to 23rd power carbon atom, etc. 1 mole of an element, 6.2 times 10 to the 23rd atom of that element.
Okay. So in the homework, we have to calculate each of the following. And in order to do so, we know that Avogadro's number is 6.022 times 10 to the 23rd power. So we are given number of C atoms and 0.500 moles of carbon. So in order to set it up, we have to make conversion factors using the Avogadro formula. So we have 0.500 mole of carbon times 6.022 times 10 to the 23rd atom of carbon all over 1 mole C. So we can go ahead and cross out like terms. So this gets eliminated as well as this, leaving us with 3.01 times 10 to the 23rd carbon atoms.
So go ahead and take your calculators out or your cell phone, see if you can get that exact number. This is where a lot of students will have problems with in the exam, so it's nice to practice correctly, see if you can get that, because I'm going to ask you how later on to be able to why are some 10 to 24, why are some 10 to 26, what do you have to do, and review again how we learn scientific notation. Go ahead, Chris.
Okay, so the next one that we have to calculate is moles. of sulfur oxide molecules and 1.28 moles of SO2. So again, we have to do a conversion factor, of course, avocado's number, and then we are given the 1.28 moles of sulfur oxide.
Sulfur dioxide.
Dioxide, yes.
Two.
Yes, forgot about that.
Okay.
So we're doing avocado number over 1 mole of sulfur dioxide. So this cancels out as well as this, leaving us with 1.28 times 6.022 times 10 to the 23rd molecules. And that should yield 7.71 times
See
10
if
to the
you actually
23rd.
get those same numbers, right? Okay. Okay. And why there are three significant figures? Because you are given 1.28 moles, and that's also three significant figures.
Right.
Now then the next.
The next one is moles of iron and 5.22 times 10 to the 22nd atoms of iron. So again, we're doing conversion factors, and we are given 5.22 times 10 to the 22nd atoms of iron. So we'll write that first. Times 1 mole of iron over, and again, the avocado's number is 6.022 times 10 to the 23rd atoms of iron. So we eliminate like terms, so we have atoms of iron that will cancel out with the other atoms of iron, leaving us with 5.22 times 10 to the 22nd times 1 mole of iron. And you should get this number if you plug it into your calculator.
Can I ask a question?
Okay, go ahead.
What did you do to calculate the mole of the iron, the mole?
Divide that
Which one?
This one?
Oh, we're given this one in the problem.
This one? So it's 5.22 times, you multiply that by 1 mole and then you divide it by this, you should get that.
I remember to keep it in three significant
And
figures.
3 significant figures, so if you, so this is 1, 2, 3 significant figures.
So you want to round
So-
it off, right?
right.
Round it off to three significant figures, so 0.08.
So basically what you do
Okay,
is
go ahead, go ahead.
5.22 times 10 to the 22 power times 1, and then you divide that by 6.
There you go, okay?
And then you divide it by the 6 point, and you're supposed to get this number.
That's two significant figures. Yeah, that's two significant figures.
8. What was it?
6, 7. Three because there's a period, right?
Yeah, but the
There's a
two zero
period.
doesn't count.
So this zero,
Because there's a period.
Yeah, but
so
the
this
two zero
zero,
doesn't count.
this one counts. This
No. That one doesn't count.
It doesn't count.
I had 6, 7.
That one doesn't count.
Okay, 6, 7.
Okay. So I was right, okay.
Because leading zeros
Oh,
may
yes,
or may
that's
not
right.
count.
That's right. Depending.
You guys have me second guess.
Okay,
So you
okay.
understand,
Okay.
you understand,
That's why it's really important to go over. So this is great. Now let's look at the next one.
take it away.
They only got one more example.
Okay. So the mole of carbon 2, hydrogen 6, oxygen in 8.50 times 10 to the 34 molecules of carbon 2, hydrogen 6, oxygen 8.50 times 10 to the 34 molecules of carbon 2, hydrogen 6, oxygen times 1 mole and the same carbon 2, hydrogen 6, oxygen.
C2H6, oh, we'll have to figure out what we call this, right? We haven't learned it yet.
Now we Okay,
Later on in
so
this chapter.
this one is divided by, because they asked for mole, I think they asked for mole. We want to give them by the answer in mole, so you convert it, and then
So your answer
Multiply.
in your can you do one in your calculator and see what your calculator spits out? Do the math, 8.5 times divide. Just 8.5 Yeah, times 10 to the 24 divided by 6.02 times 10 to the 23rd. So you get 14.
1.41119.
Okay, so you got 1.4, but because it's 10 to the 24, so we need to learn to manipulate, right? How do you manipulate? So what you get in your calculator is 1.4.
1196.
1.4196 times 10 to the 1, right?
It says
what do you get?
E47.
Yeah, I got 47 too.
What?
47 as the exponent.
10 to the power 47. But don't you just carry the power right there, so it'd just be...
No, it's 8.5 times 10 to the 24 divided by 6.02
Oh, yeah, you're right. So
times 10 to the 23rd, right?
Yeah.
So it takes like...
Yeah, that's what I got.
Divided by, plus 24? Sorry. Wrong entry. It cannot be 24.
And then that's the answer divided by 6.02 10 to the 23rd.
23rd. Yeah, that's gotta be wrong.
Is that a homework problem? Is that
Yeah, it's a So because this is 14, right? How did they get 14.1? Because of this 1, right? So then we just move it because I'm sent to the 1, so then it's 14.1. So that's how you get 14.1. Okay?
Oh.
So that should be correct. But this is what you should get. Calculation
Yeah.
was, see?
Yeah, that's right. 8.5 times 10 to the 24 divided by 6.02.
So when you solve problems that deal with exponents, make sure that when you see, okay, 24 and 23, and you're not getting 47, this is not right, because I should be getting like 1.
Yeah.
So that's what it is. So these are common mistakes that students will tend to make. It's not a chemistry problem, it's a math problem, but that seems to be for chapters 1 through 8. This general chemistry section of 1032 is very, very important to understand. Okay? Okay, so go ahead. So Rania,
Okay. Basically, when I was doing this as a homework, I kind of had difficulty knowing where to put the 6.023 or when to put the mole. Just basically look at the question, what is it asking you? You write it down and then you just like match it up. Like, okay, for example, it's asking for 8.50 times 10 to the 24th power moles of C2H60. Just take Avogadro's number and then match it up and then cancel it and do the math and so on and so forth. Because when I first started off with the problems, I used to always just put the number on the bottom and just kept doing it after getting it wrong so many times.
yeah. So these are good, from experience as she was learning to do the homework. Today she just found out. What I want to reiterate again, when you say items, right? So it can be atoms. So like carbon atoms, it can be molecules, like sulfur dioxide molecules, right? But then it can also be a sodium plus ion, and later on we'll learn that that's a cation, and it can also be a chloride ion, we refer to as an anion. So very important, can be atoms, molecules, ion, cation, and ion. So the items are very, very important. So if this happens to be, this is an iron atom, right? But it can be iron 2 plus or an iron 3 plus. So it can be Avogadro's number of ions. It's also very important. Do you want to add anything else? So that's really good, right? Let's give them a hand. Awesome. Okay, so let's go to 5.2, and we have introduce yourself.
Hi, I'm Jennifer, and this is Sandy, and we're going to go over 5.2. Okay, so 5.2 consists of molar mass, and we're just elaborating a little bit on what Avogadro's number is. For molar mass, it's for any element that the quantity called molar mass is the quantity in grams that equals the atomic mass. So it means, like, for instance, if you look at the carbon element, one molecule of carbon equals 12 grams, which is the same thing as its molar mass. Okay, so how we did the conversion was that this is Avogadro's number, so it's the number of elements. So 1 mole of carbon is 12 grams, which is that 1 mole of carbon is 12 grams, and 1 mole of carbon is 12 grams, which also means that it's the same amount of the Avogadro's number, or the number of atoms. So 6.02 times 10 to the 23rd atoms of carbon equals 1 mole of carbon, which also equals 12 grams of carbon. So they're all interchangeable. Okay? And Sandy's going to explain how to calculate the molar mass of a compound.
To calculate the molar mass of a compound, you first have to obtain the mass of each element, then you times it by the number of the element, then you add them up. You have an example right here. For water, we have 2 waters, 2 hydrogens. So it's gonna be 1 is the mass times the number of the hydrogen, which is 2. Then you have oxygen, which is the mass is 16 times just we only have 1, which is 16, and we add them up, it's 18.
How about the group doing an exercise of carbon dioxide, CO2? And then raise your hands when you got your answer. You guys? Yeah.
We have other people who will be.
Yeah. You wanna do that, Anthony?
You want to do it? Yeah.
I can do it. Remember, how do you do carbon dioxide? You get the 20 points, you have to percent, right? Make sure everyone else has to do this because it's the best.
If somebody else do it, you're gonna give us 20 points?
Yeah, 44.
It's very, very clear now, right? Everyone should be able to calculate the molar mass as Jessica and Jennifer and Sandy showed you. So that's how you will calculate the molar mass of carbon dioxide, right? There's 1 carbon and there's 2 oxygen. This is your periodic table. So this is much easier than the mole calculation of moles. Okay, thank you. Good job. So now we have 5.3, right? So we have Sheldon. And who is in group 3? Anyone else is in group 3 with Sheldon? Okay, so let's listen up to Sheldon.
So I have 5.3. Basically touches on 2 points, chemical reaction equations. Chemical reaction, and it touches on chemical equations. Chemical reaction involves a change because of atom reacting to substance. It forms a new substance. An example of that is rust. Whenever it rains, or I don't know if you ever seen like flower pots outside, it just builds up that rust on the bottom part. So that's a chemical reaction, and that's a chemical reaction taking place. The chemical equation, it touches on just reactants and the product. basically what it's going to take to balance the equation. The arrow forms, has some examples in the textbooks there, the arrow and the forms of the product. The product's on the right, and
Yeah, so we have an example here, right?
yeah, the reactant atoms, and then it goes into the product atoms.
So, because we learned that matter can neither be created nor destroyed, right? So we can actually prove that the starting material is called reactants. The number of grams of reactants that start should equal the number of grams of product that are formed.
Pretty much.
So the moles,
Yeah.
grams.
So it was a short section, so, you know.
Good job. Okay, so Fiorella and your group, Martha, Chitana, Mike. Yeah. So they have the different types of chemical reactions. Okay. So, raise again. Go ahead, Fiorella.
So we have section 5.4, which is chemical quantities and reaction. My name's Fiorella, that's Martha, Maurice, Natalie, and Chitana. Basically, I'll start off with the beginning of the section, which is combination reactions. It's two or more elements or compounds bond to form one product. Basically, you have A, you have B, put it together, you have AB. Here's an example of sulfur and oxygen. You have one of each to make sulfur dioxide. That's a quick example of that.
Just a point, right? Why is it O2 and not O? Remember, O2 is a gas, and we learned that diatomic molecules tend to stay as O2, N2. Gases tend to be diatomic, so that's right.
And if you open to page 189, there's also a really good example of magnesium and chloride and what makes it magnesium and chloride together. So,
Okay. So the next one is decomposition, which is one substance that splits into two or more similar substances, which is AB equals A plus B. So carbon and chloride 2, which is a solid, makes carbon plus
Calcium.
calcium and plus chloride 2, which is a gas.
Okay.
You're just putting AB to make 2 together.
The single replacement is basically you have one group and it switches with another group. Kind of like boy is with this girl, he dumps up and get with this girl and yeah. And that's the single replacement.
Good example, huh? Okay. Very nice.
And then the double replacement.
Okay, and then the double replacement is two elements in a reaction, which is AB plus CD, and now it switches, it's almost like a foil effect, which is AD plus CB. So that's basically what the double replacement is.
And this is an example of showing you this is A, B, C, D, and when you do it, this is A, D, C, B.
So you notice that the plus of one reactant will combine with the minus of the other reactant. Okay?
And then we have combustion reaction, which is a carbon-containing compound, usually a fuel burning oxygen from the air to produce carbon dioxide. I have an example just to show you guys how it's done. It's CH4 plus O2. Then we're gonna try to make both sides balance. It's gonna be CO2 plus 2 H2O. On this side we have one carbon, and on this side we also have one. Here we have 4 hydrogen, and also here 2 times 2 give us 4. And here we have 2 oxygen, and here we have 2 and 2, which makes it a total of 4. Just to make it even, we're just gonna add the 2 here, just to make it 4 and 4. That's it.
Really good, right? So you want to learn that matter can neither be created nor destroyed again, so the number of reactants, moles, should equal the number of reactants products moles also. And the difference between a combustion reaction and a combination reaction, this happens to be this can also be classified as a combustion because it's oxygen, but you can go ahead and write down your magnesium and the chloride, because that's also, sometimes the book gives us confusing concepts sometimes. Combustion is a form of combination. Combination more or less encompasses, they also refer to combination reactions as synthesis reactions because you're making a new substance, you're combining something. But combustion is mostly a reaction. So Natalie gave an example of methane, right? This is how methane is combusted or broken down when we burn it. So did you write down? Oh yeah, it's over here. So here was on what page?
189.
189 in your textbooks. Take a quick look at that also, where you have magnesium, and we'll be doing this. We actually do this in the lab. We have a magnesium ribbon, magnesium metal, very shiny, and then just light it, and then all of a sudden you have an intense flame, really white flame. And then after that, when it burns out, you have a gray powder. Yeah, gray ash. And so that's your magnesium chloride, kind of ash, but then it gives off some form. But you have magnesium chloride. Okay, so any questions?
It was a pretty easy chapter.
Yeah.
When you guys read over it, it's not that bad.
And there's examples on page 80,
There are more
87,
examples.
so it's pretty easy.
You will note from the pre-lecture PowerPoints, very easy in the next exam. Make sure you recognize a decomposition from a combination, recognize a double replacement from a single replacement. Okay? So 5.5, very good, baby. Let's see, 5.5, okay, come on, gentlemen. So we actually have, what do we have here? Cynthia, Jared, Vernon, and Charles. So, come on over. Let's start talking. So, this is actually one of the really tough topics here. Come on, you can do it. Yeah. Okay.
Okay, hi, my name is Cynthia, and this is
Berlin.
And Charles.
Alright, so we have oxidation, reduction, reaction. Oxidation, by definition, it's loss of electrons. That means if you have something, you lost some of it, that's a loss. Okay? Reduction, gain of electrons. So if you have, say you have $5 and your other friends have $4, and then since you have more, we'll say we can go by 8. He has 7, he has 9, I have 7. So if I want to gain 1 electron, I can just take one for him to make it 8. So an example of it is sodium. This one, okay, so we did the okay, and this one basically, she gave you an example where we have oxidation, and sodium in this one basically gain 1 electron. And in this one, this is the reduction where we have ferrosulfate, iron basically, that actually gain 2 electrons, and on this side, close to electron. That's about it.
Can someone clarify this?
passage that, like, we should study a little bit more on the part where it says lose electron, gain electron, how many you gain, how many you lose. For oxidation, it says nonmetals gain electrons to form negative, and metals lose electrons to form positive. So we can say metals are always oxidized and nonmetals are reduced.
So you can say loss of electrons, lose electrons is oxidation, Leo, right? Okay. And then what does the line say? Grr, right? Gain of an electron is reduction. So that's how you remember it. Okay? So do we have any questions? Do we have any homework problems similar to this? Because this is actually a tough topic to I know Chris and Michelle, you probably have some, right? I corrected your word. So thank you. Okay, so now we have 5.6. Okay, so Marcella, introduce your group. And everyone else stand up. Yeah, I wish, I hope, can you all see them from up here? No, I see. And then, who's 5.7? Who's 5.7? You have 5.7?
Actually, 5.7?
Yeah.
That's how, I know. That's how we look at it.
And 5.7, right?
Oh, well, we're not 5.7.
Oh, no.
5.7 over here.
No, we're not 5.7.
No, who is? Anyone?
I don't think anyone is. I need someone to finish with 5.7. I have to take teacher's phone here, no?
Yeah, but you guys keep it together. Yeah, I can do that.
Pamela, Tamara, and Michaela. And we're going to be doing section 5.6, which is based on mole relationship and chemical equation. It's pretty simple. We're going to be breaking it down for you guys in a few seconds. The most important point in this section is the law of conservation of mass. What the law of conservation of mass is, it states that there is no change in the total mass of the substance reacting in a chemical reaction. There is no change, nothing is gained, nothing is lost. No material is lost or gained when a regular substance or changed to new substances. We have some few examples here. Michaela will be explaining them.
Yeah, for example, the substance on this equation, which is two silver atoms and one sulfur equals two silver and one sulfur, meaning you cannot lose or gain any more than what there is. And then they also talk about mole to mole factors in equations, which they're just saying technically that the ratio always going to stay the same, but you might make use of some of the substances. But technically that the ratio always stays the same. Like for example, in the iron and the sulfur equation.
And on page 194, you see that there's a chart here available to balance the equation.
Any questions? Very good, ladies. Okay.
I'm just gonna try.
You want to start writing? While Katsia is writing 5.7, we are...
Renee?
So pretty much a chemical reaction it's what takes place to break up the atom. The molecule of the reactant must collide with each other and have proper orientation so they can go and break. That energy to break the atoms apart is activation energy. Activation energy is the amount required to break the bond between atoms of the reactant. It's analogous to moving up a hill, so think of you climbing to get that energy up there, and as soon as you're there, you can just slide all the way down. 3 conditions required for reactions to occur.
We have collision, orientation, and energy.
Like for example, after that, we have two reactions, which is exothermic and endothermic. I can take like for an example, like the hot pack in the hospital, when they add the hot pack, when they take the calcium chloride, they add it with water, and the reaction can be, I'm sorry, can I do it in here? Yes, yes, yes. Okay.
There you go.
Okay, for the exothermic, when we add the carbon chloride, which is CaCl2, we add some water on it, which is hydrozole, and the reaction that is gonna release, energy. So the reaction is gonna be CaCl2 plus 81 kJ. This is this is the exothermic of the hot pack in the hospital. And for endothermic, this one is okay. For endothermic, they add ammonium nitrate, which is NH4 NO3. But this one already release the energy, which is 26. Yeah, which is 26 kJ. And for the endothermic absorb the energy. So the reaction is gonna be this is the ammonium nitrate for the cold packet at the hospital. Like for example, the cold packet, when you have like your muscles is released, or they would like to put a cold, yes. Jonas? Okay, you know this. They just like to release the muscles. They can just put the cold packet, and then in order for the muscles to release and the capillary to flow the blood easily.
We're gonna go back to 3 conditions required for reactions to occur, just so you can get a little information on that. Reactants must collide with each other. So think of gas. When exothermic is occurring, all the heat is causing the gas molecules to move around faster. They'll collide. They must align, and the energy of activation must occur for it to have the energy to break the bonds again. Now we're going to move on to rate of reaction. The rate of reaction is measured by the amount of reactant used up, the amount of product formed in a certain period of time. Would you like to go ahead and follow along with that?
Low activation energies makes it go faster. High activation energies make it go slower. So these are affected by changes in temperature, changes in concentrations, or catalysts. For example, if you want food to cook quicker, you turn up the heat. You want things to go slower, you lower the temperature. Yeah.
Concentration of reactant. Rate of reaction is also increased. No reactant are added, which is in turn causes more collisions, resulting in a faster reaction. So, as you increase the heat, basically, as you're increasing like boiling water, as you increase the heat, the water tends to boil a lot faster, and you see most things coming out if it's colder. That's basically it's kind of related to this one as well.
You can also take vinegar and baking soda. If you add the vinegar to the baking soda to the vinegar, it'll automatically start to funnel and make that volcano science project. If you do it the opposite way around, it won't cause such a reaction for it. So, catalyst is another way to speed up the reactant. It's like a shortcut. You can take the activation energy, which is going up the hill, and take an example of catalyst going through the hill. And instead of having to spend that energy, you slash it in half. And the human body, we have biocatalysts called enzymes. Those are what makes the metabolic reaction in our body able to keep up to cellular activity at a certain rate. That's it.
Very good. Tough section, right? So I'll fire up our 5.7 and the PowerPoint also.
5.7 is mostly about conversion, molar to molar mass. So here I put like 3 examples of how to convert. The first one is molar mass, and how you just do it. The first group did it already. You put the first, whatever is given on top and what you needed on the bottom, cross over so you could get what you need. That's the first example. And the second one is mole to mole, and mole, whatever you need, mole will be face each other so you could get your result when you need it. Same, go for it for this one. It's actually, they will give you one substance and you have to find the other one. Okay, so whatever is given, you use first, and what's needed, whatever you need, you put it here. What's needed will go on top of the division line. So you could cross over and get your answer. And here is it's actually.
We want to come over here now to see and use the PowerPoint. See if you can. Because you know the topic, so come over here. I'm putting Katsi on the spot here, right? That is great.
Yeah, so here, okay, so the reaction between hydrogen and oxygen is 13.1 gram of water. So we will use hydrogen plus the gram will use 13.1 and is that right? And this will be the result.
Okay, good job. Okay. So you will want to think of all the different sections that we just discussed, right? So 5.1 is mole. So you immediately think of Avogadro's number, right? Atoms, molecules, ions. And then 5.2, molar mass. So think of Jennifer and Cindy. Right? You can think of it that way. Start creating, how can you remember certain things? You can make some imagery, association, right? And then what's 5.3? Equations, right? Chemical equations. So what's a chemical equation? What chemical equation can you think of, like right now?
Water.
Okay. How do we make water? We have H2 plus O2 gives you H2O, right?
Yeah,
So think of
hydrogen and oxygen.
Yeah. Okay, so think of chemical reactions right away, and you see how Nathaniel showed you how to balance with the combustion of methane, right? CH4 plus oxygen, okay? So that's how you want to study science. Studying science is not like reading a novel, right? You almost have to write. I know with me, I still have to write down so that I want to see that I can bring coordination. And once again, the students that do their homeworks way ahead of time, and I've checked about 30% of you, they're the ones that tend to actually get the A's also, because you're engaging your brain so many times, even before our lecture. And that's why I thought after our exam 1 last week to do a pre-lecture of exam 5, because doing the math chemical quantities, you noticed how tough it was to get tripped on calculating Avogadro's number, right? Yeah. So make sure you can repeat those calculations of the Avogadro's number of moles, because the chemists weigh in grams. Hence we have the grams molar mass connection relationship, right, in 5.2. Now we got to bring everything into a chemical equation. So when we talk about chemical equations, like the equations that were being talked about in 5.8, if I wrote this textbook, I would have started with a macro world. I would have started with 5.8, the endothermic and the exothermic. Because what you do when you're in the hospital, right? You want a cold pack, so you have this ammonium nitrate, like Sanjay was talking about, right? So one side has ammonium nitrate, the other side has this water. You pop those, they mix, it gets cold, and there's the kilojoules, right? The hot pack's the same way, gives off heat. But when you say activation energy, it's probably hard to visualize what activation energy is, right? So let me go back to that PowerPoint slide. So in a sense, I'm trying to summarize the chapter. If I was teaching this, I would have started with this section, 5.8 instead of the mole 5.1, and then go backwards and end up with the mole, right? But different authors have different takes. And just like Alex said, before you can have a chemical reaction, you have to have that collision, right? And of course, the orientation too, because how can you get a chemical reaction if these are the only active parts that will, when it collides, or will make the chemical reaction, and a collision like this and no chemical reaction. So that's what orientation is all about also. And then when it says energy of activation, when it's exothermic, this is what you have to know, that it gives off heat, and so hence the heat in the form of kilocalories, right? So the plot of energy will go with time will go down. Well, it's the opposite for the endothermic. Okay, so still visualize the shape also, right? This is a cold pack. That's a hot pack. You see? No, you're good. No, you're good. It tells me that you are actually. Yeah, but there's something, right? Yeah, something before you put this, right? So this cancels, right? Yeah. Now we want moles of nitrogen to cancel, alright? So now we got a moles nitrogen over here. Yeah. And you want to put that in the denominator. Yeah, 2 moles NH3 over 1 mole of nitrogen. You see that? Over here.
17292?
No. Just put 1 mole and 2. 1 mole. Yeah, that's good. 1 mole and 2. Oh, okay. And then now you put what you just did. That this cancels. That cancels. You see that, right? Did everyone? That's the most important one for. So try to write for those that. Are you seeing what Sanjay's doing, right? Yeah, but now you will know. We can do it better. This is called the mole bridge. Very important. So finish. You're not done yet. Oh, okay. So the result. So remember. So we have 28.
Oh, yeah. Oh, okay, it's 1.1.
Yeah, we need to change that, right? Yeah. So how can we fix this? Who knows how to fix this? Anthony, you want to help? We need to fix this, right?
The last part,
This one, come on, let's see that, I'll fix it.
We multiply this one by this one.
This is good, right? Fix it. Good.
Okay.
Yeah. So, thank you, Sanjeev. You got some
extra credit,
extra points. Yeah. There you go. And then you do the math, and what do you get? Right? And see how easy it is instead of all those, right? You see?
Wait, where does the 17 come from?
17 grams of ammonia, the molar mass.
Gotcha.
17 is the molar mass, right? 17 molar. Okay, so you will see one or two questions like that. But when you'll be dosing, right, especially as a nurse, you'll be doing all sorts of calculations all the time, so you want to be comfortable. And this exercises your brain, right? Neurons that work together, act together, fire together. So you're developing your long-term memory in your frontal cortex. It's just short-term memory over here, it needs to go over here, so you remember it for exam 2 in 4 weeks. So practice. 2 weeks, yeah, my bad. Okay, so that's one of the important things that you need to remember.
Oh, okay.
And so now everything just falls into place, actually, right? So just to show you, right? So for those of you, how many of you have real silver utensils, right? Spoons and forks, right? They're very shiny, right? So yeah. Okay, but then when it tarnishes, right, it turns into silver sulfide, actually black. So that's kind of the composition of silver sulfide, Ag2S. And so 2 silver plus sulfur, right, which is Ag2S low relationships and chemical equations. So law of conservation of mass, matter can neither be created nor destroyed, nor energy can neither be created or destroyed. So the energy is also going to play, have to be the same for the products and the reactants. So make sure you remember that 2 silver atoms plus a sulfur atom gives you tarnish, silver tarnish. Okay? And so I think I need to lower because I have all this writing on the board, right, that you cannot see. And sometimes I write on that. So just to review again, here's our silver tarnish, right? So take a look, the equation. So this is referred to as our chemical equation. 2 moles of silver react with a mole of sulfur to form a mole of silver sulfide, silver tarnish. So there are 2 silver atoms and 1 sulfur atom to form silver sulfide, and because it's ionic, right, we call it a formula unit. And then how many Avogadro's number are there? So it'll be 2 times 6.02 times 1023rd also. Or how many sulfur atoms would be Avogadro's number? How many silver sulfide atoms? It would be Avogadro's number of silver sulfide atoms also. But then when you look at the chemical equation, what does it tell us? The chemical equation says 2 moles of silver. So that's why you have 2 moles of silver react with 1 mole of sulfur to give you 1 mole of silver sulfide. So you'll want to understand how the problems could be written at, right? You could say atoms, molecules, moles, and then to determine the molar mass, make sure you, in fact, know actually how to determine the molar mass. And this is proof that matter can either be created or destroyed. From the balanced equation, you come up with the total mass of the reactant starting material and the total mass of product.